The lean development system is based on 5 basic principles. First, focus everything you do on creating value. Usually in development, that value is in the form of usable knowledge. Second, lead with entrepreneur system designers, people who will treat each project as the creation of a new business. Third, create team-responsible experts, people who will take full responsibility and are genuinely expert at doing it. Fourth, practice set-based innovation. Look at multiple alternatives and narrow them down over time by aggressively attacking them with tests and simulation. And finally, create flow, a rhythmic process that enables the system to work well and smoothly despite the chaos and turbulence that are part of development. Trade-off curves, or more accurately, trade-off curve pages, the complete information that goes along with trade-off curves, fall into the category of creating usable knowledge. In fact, they're one of the 2 major elements, the other being the elimination of waste. They are the primary tool that lean organizations can use to create effective knowledge that they can use over and over so that their specialized expertise becomes their primary asset. The Wright brothers had a problem. They wanted to design a machine which had killed all of the previous important investigators. All of the previous important investigators of heavier-than-air flying craft had died in stall crashes. So the Wright brothers couldn't follow a design and then test methodology. Testing was fatal. They had to not only invent the airplane, in some ways that was the easy part, they had to invent aeronautical engineering, and they had to invent a new way to do engineering. Instead of design and then test, they tested and then designed. They systematically evaluated all of the features of the aircraft before they designed and built one. They were the first to use wind tunnels to study the performance of airfoils. They were the first to systematically design a propeller. And most important, they were the first to design a control system for the aircraft that did not depend on shifting body weight. The results are, of course, well known. But the intermediate results, the ones that made the final flying aircraft possible, were sets of tables which listed the effects of changing parameters on the performance of the various parts of the airplane, not the airplane as a whole, but the pieces. They were, in fact, although in tabular form, not visual form, trade-off curves. As nearly as I can tell, the story of trade-off curves is basically the story of the American aircraft industry. Trade-off curves came into existence with the Wright brothers, were responsible for some dramatic successes during World War II, and then disappeared after World War II. Between World War I and World War II, the community of aviation enthusiasts and industrialists had a lot of enthusiasm and a lot of talent, but not much money. So they spent a lot of their time investigating fundamental issues and recording those results in the form generally of trade-off curves. For example, the National Aeronautics Advisory Committee, the NACA, published catalogs of airfoils. These listed the coefficient of lift versus the coefficient of drag at different Reynolds numbers. One thing to notice here is how much compression of data there is in the form of this catalog. Reynolds number, coefficient of lift, and coefficient of drag are each functions of 4 or 5 different variables. So there's a lot of information here, which enables us to compare airfoils of very different sizes under very different conditions and still use the same table, the same airfoil, the same trade-off curve. The P-51 Mustang story is a remarkable story. Some would say that the P-51 Mustang is the finest piston engine fighter aircraft ever built. It was designed and put into production in 1943 in 6 months, from a clean sheet of paper to rolling off the assembly line. The initial aircraft had about 1,200 horsepower and a speed of about 390 miles an hour. During the 1990s, Jose Rodriguez found some of the men who had worked on an initial design and asked them, how in the world did you do that? How could you design such a complex and effective piece of machinery and put it into production in 6 months? They said, well, first of all, of course, it was wartime, and so we were all working about 60 hours a week. But second, and more important, we already knew what all the trade-offs were. We had the trade-offs recorded in the form of nomographs for every important aspect of the aircraft. Designing the aircraft, then, was simply a matter of deciding where we needed to be in the trade-off space. Then, they said, because of course they were all young at the time, then we got computers, and now it takes us 20 years to design a fighter aircraft and put it into production. So now we come to the paradox. If trade-off curves are so effective, why did they disappear almost completely from American industry in general, and the American aircraft industry in particular, after World War II? After all, the P-51 Mustang was designed and brought into production in 6 months. It now takes us 20 years to do a fighter airplane. Could be that it's because of increased complexity, but in fact we know from the experience of the Lockheed Skunk Works that some very fine aircraft in fact were designed and put in production in only 2 years. So it's not primarily a complexity problem. Here's my guess. It's a process problem. Computers made it possible to design and then simulate aircraft safely. You couldn't design and test them. It killed the test pilots. But you could design and simulate them. It didn't matter if they crashed in the computer. This fit well into the way the Air Force contracted for aircraft, because they contracted on a project basis. They didn't want to spend a lot of money developing basic understanding. As a result, then, the aircraft industry has increasingly moved to a design then simulate system rather than doing the hard work of understanding how to formulate the trade-off curves and then designing things that will work. The final most exciting example is probably the Boeing 777, which has been touted as an enormous design success because the aircraft was done entirely in simulation. There was a complete assembly simulation of the aircraft done, and the very first prototype was sold on the market. What Boeing doesn't talk about very much is that the 777 is by far the most expensive development process Boeing ever did. So, Toyota is left with a difficult problem. They know they have to get better at using computers, but they're afraid that as computers become more widely used, engineers will begin to lose their intuitions, and design performance will actually decrease. Notice that Toyota has been able to build cars without prototypes, which no other car company can do, through the use primarily of trade-off curves, not the use of computers. Toyota isn't really very good at simulation right now. So Toyota has the problem of introducing more simulation while not losing the basic understanding. Most US companies have the opposite problem. They're okay at simulation. What they need to be good at is basic understanding. And that, of course, is what trade-off curves are for. The first trade-off curve that I saw was at the very first interview that I had with a Toyota supplier. It's only taken me about 10 years to figure out how important it was. That supplier was Sango. I had gone to Japan looking for evidence of set-based innovation because my research in design automation had convinced me that looking at multiple alternatives and killing the bad ones was a better way to do design than looking at a single alternative and then making changes to it. That worked so well for computers, I thought maybe humans should do it that way too, and I thought maybe it was being done that way in Japan. So I went to talk to Nissan. And the folks at Nissan said, "What, are you crazy? We design one. Why would we design more than one? That sounds expensive." Then I went to Mazda, and they said the same thing. I was getting pretty desperate, but I finally went to Sango, which supplies exhaust systems to Toyota. And I said, "How many exhaust systems do you supply, or do you design, for a single Toyota?" They said, "Well, normally, while Toyota's developing the car, we will prototype 10 to 20 exhaust systems. Sometimes we've done as many as 50. I heaved a big sigh of relief. That meant that I wasn't going to have to pay the money back to the Air Force, and my student was going to be able to get his PhD. And then I said the obvious question, "Why do you do that? That sounds expensive." And they said, "Well, we do it because Toyota makes us do it." And I said, "Well, Toyota's paying for it sooner or later, one way or another. Why does Toyota make you do it?" And they said the chief engineer, the project leader, wants to know what the trade-offs are. I said, "What do you mean?" And they said, "Well, let us show you." They said, "What we're trying to do with an exhaust system is to reduce the noise." However, in order to reduce the noise, we create back pressure in the exhaust and the gas as it flows out of the engine. Therefore, there's a trade-off between reducing the noise and creating the back pressure, and the back pressure reduces the performance of the engine. We can show that trade-off as a curve. Above that curve, we can easily design an exhaust system that will do the job. Below and to the left of that curve, we can't do it. It's impossible. So, the project leader, the chief engineer, wants to know what that trade-off curve is. Then, he can decide where he wants to be on that curve, what kind of trade-off he wants between performance and noise for his engine. Actually, the curve that we just looked at isn't very meaningful, except for purely qualitative purposes. I want to emphasize, though, that qualitative purposes can be really important. They can help us understand, even though we don't actually have any numbers. So, to make this curve meaningful, first of all, we need to put numbers on the scale. Second, and more important, we need to have something that is general. For example, right now we're looking at noise level. Well, noise level only means something at a particular engine condition, a particular amount of noise coming out of the engine. So it would be more reasonable to actually plot noise reduction, the change in noise level as a result of adding the exhaust system. Similarly, back pressure is only meaningful at a particular flow. So it would be a lot better if we were to plot back pressure as a ratio to the amount of gas flowing through the engine. Even better, we might be able to include some indication of the volume of the exhaust system or its cost. Then we'd have a curve that was really general and could be used in a variety of circumstances. This is the art of trade-off curves. It's something that we'll consider in detail when we get to the section on advanced skills. But the important thing to understand is trade-off curves are useful in beginning to understand even before one is good at using them. But they're much, much more useful once you get good at understanding what are the variables that you need to plot. What really governs the limits of performance of your systems? That's what we're trying to find out. That's what we're trying to plot. And that's where we get the real benefit. Combining many variables into a single parameter allows us to plot a lot more information on a page. It enables us to use the same curves to describe a variety of situations so that they're useful across a much broader range. For example, in the case of the airfoil plots, the plot is of coefficient of lift and coefficient of drag with Reynolds number. This allows us to use the same plots to understand the behavior of a particular airfoil shape at a wide range of speeds and sizes. Trade-off curves work so well because they combine the power of mathematics with the power of the human visual processing system, or visual cortex. The visual cortex is the biggest single piece of the brain. Some estimates say that about half of the human brain is occupied with processing visual information. In contrast, the part of the brain that processes mathematics is really small. Human beings were not evolved to do mathematics. So, by taking mathematics and putting it into the form of visual curves, we can understand it in a way that we can't possibly understand it by looking at the equations themselves. So what are trade-off curves good for? Well, first of all, they're the primary means that Toyota uses to capture the knowledge that it's accumulated over the years. Naturally, some other information needs to go along with them. I don't want to say that it's only the curve itself, but the curve is an important part of the means of recording that knowledge. That knowledge, in turn, allows Toyota to design things right the first time. It also is a powerful tool for design reviews. Obviously, we can just look at a design and say, where's the curve? And at what point on the chart does the design fall? If it falls in the safe zone, we have a good design. If it falls in the infeasible zone, we don't. Trade-off curves are also a primary tool used in teaching new engineers. As soon as an engineer joins a section, he gets a copy of the trade-off curves for that section. And trade-off curves are used for negotiation and explanation between Toyota and its suppliers, between the different sections of Toyota, and between individuals and their managers. Last but not least, trade-off curves are a powerful tool for thinking about new designs and new issues, before we have any data, because they help us think through what do we expect to see, and that helps us figure out what kind of data we need to collect. It also helps us get started designing in the right areas of the design space. So the power of trade-off curves is that we can use them when we're thinking about the future, we can use them during the design process for the current design, and then that knowledge is available for use in the future. We just update them each time we get new data, and they gradually change to improve the performance, increase the safe zone, and decrease the infeasible zone. But we get to use them forever, and we get to use them right away. I've been making some pretty strong claims for trade-off curves, and you may be starting to ask yourself, well, what aren't they good for? Here's a couple of things. They don't do a very good job of representing issues that are basically logical. So for a lot of issues in software, for example, they can't really do you much good. They're also not much good probably for designing electronic digital logic. The second thing that they're not good for is things that are really simple. You want to design electric sockets, for example, so that people can't put their fingers in them. You don't need a trade-off curve for that. You just need a rule that says that electric sockets should always be smaller than, say, 1/8 of an inch. There's a third category, though, that's more questionable. You might assume that trade-off curves, because it's hard to show more than 3 variables on a page, are not good for complicated designs or complicated design situations. I'm not so sure that's true. If a design is so complicated that I can't understand it, then I can't put it in a trade-off curve. But if I can't understand it, can I really hope to do a good job of designing? I don't think so. So applying trade-off curves in a complex situation may require a lot of thought to figure out how to combine the variables in a sensible way to produce a set of curves that are useful, that let me really understand the design. But I think that thought is worthwhile. I think that saying, oh, it's just too complicated, we can't use trade-off curves for this, is probably a one-way ticket to a really bad design and some really severe problems down the line. There are 2 basic approaches that you can take to creating trade-off curves. One is, you can just let people do the curves that they think are important. That's not a bad thing, and in fact, it's going to be part of your strategy no matter what you do. If it's not, you're probably not going to get everything you need. But it's a good idea to start using another strategy, which is to create a list of the issues that you'd like trade-off curves for. I'd recommend that you do this as a group so that you can get group input into it, and to use one or more of 4 techniques. You can create a failure modes and a list. If you have a failure modes and effects analysis, that'll do as a start. Or you can build a function diagram or a block diagram, or just work directly from a drawing. Whatever you do, and if you have your own technique, that's fine too, balance off the requirement for enough quantity with the requirement for enough quality. That is, balance, just get it done, we can change it later, against, if we have a whole lot of junk here, it's not going to get used. In order to do this, negotiate with your people. Expect the results that you see to change. As they get into the process, they're going to learn a lot about the issues that they're dealing with, and the definition of those issues is going to change. So don't expect that what you get back will be exactly what you asked for. In fact, if it is exactly what you asked for, probably your people aren't thinking enough for themselves. I want to make several points about the trade-off curve thought process. The first is that it really is a thought process. It's not a format. I don't really care whether what you finally produce follows the framework that we're outlining here. What I care about is that you think about all of the issues involved, that you really do define what is the problem or the issue that we're trying to deal with, that you really do think through what is the basic causal situation. Why are things happening in detail? In some ways, that's the most important step. Because if you really understand in detail why things are happening, you'll be able to quickly see how to build appropriate curves in order to optimize those parts of the system. Now notice this is very different from some other ways of approaching problems, such as, for example, robust engineering. In robust engineering, we normally take the system as a whole, we pick some causal variables, we try different levels of those causal variables, and we try to optimize everything simultaneously. Normally, when we're doing trade-off curves, we aren't worried about optimizing anything. We're just worried about understanding. And to understand, we need to understand the pieces. So we need to do a good causal analysis to figure out what the pieces are and which pieces are connected together so that we can pick the right ones to develop trade-off curves for. Similarly, it's important to have a good picture. The picture enables us to apply our visual intuition to figuring out what the problem is, to seeing the causation, and to understanding what the trade-off curves mean. Okay? Again, it's not enough just to have a curve. We need to understand, why does the curve happen? What does it mean? How does it connect with the physical reality? So that's part of the thought process. When we're doing the curve itself, we'll do a lot of analysis about, okay, what's the right combination of variables? Which variables are we going to put together? Usually we won't just take one variable and plot it against another. We'll do some combination of variables because the combination of variables is more meaningful and more general. And that's part of the thought process, understanding what combinations of variables make sense. Data source, also part of the thought process. How are we going to most economically, cheaply, and quickly capture the relevant data? Usually when we're doing trade-off curves, we don't have to gather all the data in the world. We don't have to gather data in the actual environment in many cases. We can gather data in the laboratory because we're just trying to understand basic relationships in such a way that we can put them together to do the design. So the data source will allow, thinking about the data source clearly, will allow us to eliminate a whole lot of expense that we might undergo if we were just blindly gathering data. Finally, of course, the countermeasures. Once we understand the problem, then we can ask, okay, how do we prevent or avoid the problem? And that's how we wind up actually doing something. Causal analysis is thus one of the primary differences between trade-off curve thinking and some other kinds of analysis. In trade-off curve thinking, we're trying to understand the fundamentals of what causes the phenomenon that we're trying to control. We want to boil it down into the smallest pieces, draw trade-off curves for each piece, and then use those trade-off curves to design so that the system behaves the way we want it to. Thus, one causal analysis may give rise to a lot of different trade-off curves. There are a number of different ways to do a causal analysis. Y trees are probably the most commonly known. Ishikawa diagrams are another form of a Y tree, which is essentially similar. You may already have encountered these. We can now see two problems with this method of showing cause and effect. First, there's no good way in these causal diagrams to show effects that are making things better. We can show the cause of the problem, but we can't show things that would make it improve. For example, in the case of driving a nail, if we roughen the face of the hammer, perhaps by putting a crosshatch pattern on it, that will decrease the side force on the nail head when we are hitting the nail with a hammer that's slightly off angle. In order to show that on this diagram, we have to say all of that, which takes a lot of room and is kind of cumbersome. We also see that we didn't carry this analysis far enough. In fact, what controls both the angle of the head and, to a considerable degree, the direction that the head is moving is where and how we grip the handle. So this is a cause which affects both of these. We don't have a really good way of showing that. It's important to notice, though, whether we have a good way of showing it or not, we need to carry our analysis down to the way in which we grip the handle, because that's what we can control. We call this the root cause, the thing that we actually have some control over, which produces the result that we want, or the result in this case that we don't want. Both these Y trees, whether in paragraph form or in graphical form, have some problems. Nonetheless, they're a quick and easy way to do the causal analysis. A lot of people like them, and there's nothing wrong with using them. Just make sure that you carry them all the way down to the root cause. Of all the different ways of showing causal influences, influence diagrams are often the simplest in terms of speed and clarity. They're probably my favorite. To use them, we need some simple concepts. First, we should have the purpose variable, in this case, preventing lost time, near the top left. Next to it then comes the issue variable, nail bending or bent nails. Then there are the factors that cause bent nails. These are intermediate factors in the middle of the chart. On the right-hand side of the chart, we'll have the factors that control whether the intermediate variables happen, and therefore, eventually, whether we have the problem. So the right-hand side variables are the controllable variables. We use a sharp arrow to show that one variable is making the next one worse. So an increase, for example, in grip angle causes an increase in head angle, which is a bad thing, which causes an increase in nail bending. We use an arrow with a circle at the end, a circle head, to show that something is making things better. So increasing the number of training repetitions will tend to improve our swing mechanics and reduce the impact error and therefore the number of bent nails. In some cases, we'll have an arrow with no head at all. Maybe we shouldn't call it an arrow, just a line. For example, the handle shape affects the grip angle, but we don't really know how yet. As we gather more information, we'll often be able to replace the variables connected by these undesignated arrows with variables that have a direct effect one way or the other. As compared with Y trees, these influence diagrams have a major advantage. Actually, they have two major advantages. One, they let us show one variable as affecting multiple other variables. For example, the handle shape affects both the grip angle and the hand rotation. Swing mechanics affects impact error, which we have shown. It also affects head angle, which we haven't shown yet and should. We can also easily show good and bad effects, and we can show a good effect as blocking a bad effect. For example, the effect of head angle on bent nails can be reduced by increasing the friction between the hammerhead and the nail, so that the head of the nail doesn't tend to skid out just because the hammerhead is at an angle. So increasing the friction has a blocking effect between head angle and bent nails. As compared to the function diagrams, influence diagrams have the advantage of simplicity, but they have the disadvantage that they're completely dependent on the intuition of the creator to decide what variables to use. There's no systematic method for producing the right variables here. So if you find that you have trouble using them, then you should try using function diagrams. On the other hand, if you find them natural and intuitive and instinctive, well, they're fast and they're easy, so why not use them? Notice that each influence diagram will produce many trade-off curves. In fact, we could theoretically have a trade-off curve for every pair of variables that are connected by an arrow. We'll want to focus on the most important first, and we may eventually start combining variables as they cluster in the diagram. Here's the heart of the trade-off curve system, the actual thought process by which we create trade-off curves. We can also use what we'll talk about here as a format for recording trade-off curves and the other information that should go with them, but we have to be careful about that. The format is less important than the clarity of the thought process itself. Of course, if we're going to put things in a format, we may need a header, and so we'll need header information on the paper. But that's not really part of the thought process. We can talk about starting the thought process by defining the issue. What is it that we're really analyzing here? What's the problem we're trying to solve? What's the difficulty? What's the objective? What is the issue? We then need to understand what are the causal relationships that create the issue, or that drive the success of what we're trying to achieve, or that cause the problem. In order to understand those causal factors, we'll often want to iterate back and forth with an illustration. So we may move from a causal analysis in the form of some kind of tree, for example, to an illustration. Or we may combine the illustration and the causal analysis into one picture. When we understand the causes, then we're in a position to draw the curve. But of course we should understand it may be easiest to understand the causes by trying to draw a curve first. So this is an iterative process. It's not necessarily something that follows a strict sequence. In order to draw a curve, we're going to need data. So we may sketch the curve first, and then move to figuring out how we're going to get data to populate the sketch, and then move back again to create a more rigorous curve with the data included. After we have a fairly good understanding of the issue, we can start thinking about countermeasures. What are the things that we can and should do that would prevent the problem, that would make the curve unnecessary, or sometimes just that would make sure that we're staying in the safe region on the curve? Here's the interesting thing. Every time I've done this, by the time I got to the countermeasures, I realized I didn't really understand the cause. And so trying to understand the countermeasures drove me back to redoing the causal analysis, often to a redescription of what the basic issue was, a new picture, and a new curve. So it's an iterative process. We'll usually not get it right the first time, but we're putting so much information on the page that it's worth taking time to really understand it and to do it right, even if that means that we have to go through it many times. The second major point that I want to make is that the thought process is a special case of a more general thought process used in Lean. I call this thought process the lambda model, standing for go look, ask why, formulate a model, discuss, and then take action. Now, that is itself an abstraction of some ideas that Toyota talks about to include a phrase that means get up and go look, the 5 whys, asking why 5 times, not just once, plan, do, check, act, which is a phrase for make the plan, do it, then go back and check to see what happened, and take action to correct the problems, and preparing the ground by discussion, or nimawashi, a concept that means before we do something, everybody who needs the knowledge needs to go understand it. And so we have to have the communication before we take the action, the discussion, the debate. The lambda model lumps all of those together into one concept to make it quicker and easier to understand. The lambda model is also, by the way, the basis of science. That's how science works. We go look, we ask why, we formulate a model, that model gets discussed in the scientific literature, and then finally it's available for people to take action on. The trade-off curve system emphasizes, of course, the look and model portion. But actually, every time we do one of the steps in formulating a trade-off curve, we have to go through all of the steps of the lambda model. Each of those steps, however, emphasizes one or another of the lambda model steps. For example, when we're formulating the issue, well, the issue is a model, and we normally need to go look at something to understand what the issue is. But the biggest function of the issue is to give us the ability to discuss the model, to understand what it is that we're dealing with here, and explain that to other people. And of course, the issue then forms a heading that people can use to look up the model and understand. When we do a causal analysis, we're mostly asking why. So that's the why step in the lambda model. When we do an illustration, of course, we're going to look. And so we need to go look at the thing that we're illustrating in order to do the illustration, but we want the illustration itself to make it easy for someone to look at what's happening without having to actually go see the physical part in this case. Now, they still probably should if they really need to understand, but this gives them a shortcut. When we do the curve itself, we are emphasizing the modeling step. We're trying to think, what is the best model of this relationship? And so we have to think about how to connect those. In the data source, of course, that's a form of going to look. And when we get to the countermeasures, finally we're talking about, well, what actions can we take to make our issue better? So the trade-off curve system is a special case of the lambda model. The lambda model is a general idea for how we gather knowledge. Finally, we're ready to draw the curve. To do this, focus on the causal analysis. Identify the most critical variables in your causal chain and plot them against each other or against the effects that they produce. Don't worry about the minor stuff. Assume that the easy things have been done right because they will have been done right. You can do other curves for them later if you need to. Start sketching the curve right away. First, the sketch will be useful even before you have data. You may decide that you don't need data, that you know what the curve looks like, or that you can find it from a book. But if you do need data, then you'll need to figure out how to get it. And the sketch will give you some idea of what sorts of tests you can conduct. Here's the critical thing. Make use of historical data. Draw on what you've learned from the past and keep updating the curves every time you get a new datum. If you do this, they'll stay useful. If you don't, they won't. The most common reason to use an experiment to gather data rather than an analysis or simulation or historical information is that none of those works. Experiments are often the last choice. When we don't have a good enough understanding of the causality or we can't solve the math, we can do an experiment. But experiments do have advantages all of their own. First of all, having the hardware gives us a better feel for the problem and the material than anything else. If we can actually pick things up in our hands, that helps a lot. It triggers our imaginations. Second, we often find when we do an experiment that we didn't really understand what was going on. The results come out different than we expect, or we see something that we didn't expect to see at all. Thus, we can discover problems in our causal analysis that we might never find by analysis or simulation. Those tend to execute whatever we think the causality is. That's how we set the equations up. But if we misunderstood the causality, we probably won't ever know by doing analysis or simulation, and something may happen to surprise us. For this reason, it's often useful to do very open-ended experiments in which we just try to duplicate realistic situations and see what happens. Finally, experiments are often a lot cheaper than we think they should be. Remember that the same kinds of computer tools that we use to do a simulation, we can use to build hardware using computer-controlled machinery. And thus, we can often do an experiment at quite a reasonable cost. On the other hand, experiments are often slow and expensive, and they can be hard to interpret. They don't let us get inside what's going on the way an analysis or a simulation does. So if we do the experiment in a very controlled way, focusing on some very narrow issue, okay, we understand what it means, but is it realistic? On the other hand, if we do a realistic, more open-ended experiment, how do we interpret the data? What does it mean? So experiments can be more difficult to gather the information that we really need from than simulations or analysis. As we think about using experiments, we need to bear in mind that the TOX approach, doing trade-off curves, testing, then designing, gives us the opportunity often to do the tests on production hardware or even the competition's hardware. So we can do tests and gather a lot of useful data before we actually design and build any prototypes. That can save us a lot of money. It can also give us information about the real world that we may not be able to get using a prototype. Except for countermeasures, everything on the trade-off curve page focuses on understanding a problem. The countermeasures tell us what to do about the problem. We don't want to just look at how to move along the curve. We also want to look at how to change the position of the curve, or how to make the curve irrelevant, how to do something that will completely change the situation. This then enables the users of the trade-off curve page to figure out what to do when they can't design within the safe region of the trade-off curve. By the time you've mastered this material, you'll be able to completely change your design process. First, all of the really specialized knowledge that you and your company have gathered, the knowledge that makes your company special, that enables you to really accomplish things, you will be able to capture in a clear, simple, understandable, and organized form so that everyone can use it. You'll find that that knowledge becomes the company's crown jewels. Then you'll be able to use that knowledge to quickly design products and manufacturing systems that work, not designed by guess and then hope that you pass the tests, but rather design things that you know will work. You may not even have to test at all. You'll also be able to use those same tools to evaluate the quality of the design at a glance, so the design reviews become quick, efficient, and effective. And finally, you'll be able to use that same knowledge to train new people, to bring them up to speed so that they rapidly become effective contributors.